Okay, so continuing with 4.3, we can now just start discussing applications to binomial experiments. So how do we compute the probability? So after we meet those four criteria, we say, okay, we have it, so what do I do now? There is a definitive function or formula for a binomial experiment. And it's here in this little box here. And we can see that there's a combination formula in there, the probability of success and the probability of failure. And notice it's going to be n choose x. So n trials choose x successful trials, right, to your random variable. And then the probability of success to those number of trials that were successful times the probability of failure of n minus x. And so this is a pretty complicated formula, especially when the problems become more complicated, right? And so we're going to go ahead and use the calculator for the calculations. You don't have to. You could use the formula by hand if you like. I wouldn't. We have binomial in our calculator and it's very useful. So let's try a simple example that's below. It says, according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. Suppose there is a random sample of 20 car-owning households. What is the probability that exactly 5 households have 3 or more cars, and round to 4 decimal places? So notice it doesn't tell us anywhere that it's a binomial experiment. And in fact, how would I know? So the only thing that I would probably see is the criteria that is involved. So let me go ahead and put the criteria over here on the margin. So the first one is a fixed number of trials. So are there a fixed number of trials? Am I just surveying like the flights, the airline that wanted to see the flights that were not on time? Am I just surveying households until I get a certain amount of households that are successful? Or am I only surveying a certain number of households? So, and it says right here that suppose there is a random sample of 20 car owning households. So I know I have a fixed number of households that I'm surveying. So n is going to equal 20. Okay, the second criteria asks if the trials are independent. Well, if your household owns 3 or more cars, does that mean your neighbor has to own or is going to own 3 or more cars? No, right? It's independent. So these trials are, each of them are independent. Independent. Okay, number 3 is mutually exclusive, right? Can a car, 2 households, that if that household earns 3 or more cars at the same time, another house is going to own 3 or more cars? No, not all the time. Like sometimes you'll see households with 3 or more cars at the same time, but not always. And that's what makes it mutually exclusive. It's not all the time. And I mean, it kind of makes sense because each household does their own thing. So it seems like it would be mutually exclusive and independent anyways. The last part is the probability of success, where the probability of success is fixed for each trial. So when they did the survey, they saw that 35% of all car owning households have 3 or more cars. So the probability of success, meaning if the household surveyed owns 3 or more cars, that probability of success is 35%, no matter which household you go to, which means the probability of failure is going to be 0.65. So all 4 criteria are met, and therefore this is a binomial experiment. Most of the time we'll tell you, but as you can move on to research methods courses or higher statistics courses, you'll have to go ahead and mentally evaluate and see if the criteria is met for it. All right, so let's go ahead and answer the question. It says, what is the probability that exactly 5 households? Well, that means that the random variable is the event of success, so households own 3 or more cars. And we want to see the probability of when the event is exactly 5. So if you can remember those tables that we had way in the beginning here, and see the list in the probability distribution. So these are each trial, right? And a fixed number of trial, 5. So we're looking for, this is the Netflix example, but we're looking for something on this table it's similar, except it's only binomial because it meets those 4 criteria. So the probability of the event, it's exactly 5 households out of the 20, right, that own 3 or more cars is going to be equal to, well, 20 choose 5 times the probability of success, which is 0.35, to the 5th power, times the probability of failure, 0.65, to the n minus x, so 20 minus 5. Okay, so we can put that in the calculator. Let me go ahead and clear this. So we're going to have math, probability 3, 20 choose 5, times the probability of success, 0.35, to the x power, which is 5th, times the probability of failure to n minus x, so 20 minus 5, which is 15, and hit enter. So you can see that the probability in which that exactly 5 households will own 3 or more cars in a sample of 20 is 0.1272. Or 12.72%. So you can do it in the calculator just like this. But however, your calculator has a binomial probability distribution in its menu. So it's super awesome. And we wouldn't have to go through all of this. In fact, we would just need to know the number of trials, the number of successes, and the probability of success. And so the first thing we'll do is we'll go to the calculator and we'll go to second vars. So second vars, and scroll all the way down until you see binom PDF. So binom PDF means binomial probability distribution function. So it's exactly, I always say, like, mathematicians aren't creative, so that's what we do. Hit enter. It's going to ask for your number of trials, which we know is 20. The probability of success, which is 0.35. And we want to know exactly 5. And paste. And hit enter. And notice these two are the same. So you just need to know, if you want to use the calculator with the binom PDF function, you need to know NPX. Now, the one thing we have to note about this particular binom PDF, this is when the probability is x equal to some number of trial. And I guess I could write it like the big X, which is the event of success, is equal to a little x. In our case above, it was the probability of x equal to 5. So when it's equal, that's when you can use this. Only when it's equal, you'll use binom PDF. Well, let's talk about another case, almost similar to the Netflix case. It says, using the same example, what is the probability that less than 4 cars have 3 or more cars? Okay, so let me transfer some information down here. We said there were 20 households. The probability of success was 0.35. And in this case, we're looking for less than 4. So we can recall our inequality worksheet. That means that little x will be equal to 4, and then big X, in the event, remember that a household has 3 or more cars, is going to be less than, strictly less than, little x, which is 4. So let me put this in perspective. What we're trying to find is when the probability of the probability that is less than 4 households has 3 or more cars is when the event of success, and when you have a household 3 or more cars, is strictly less than 4. So this either means a couple of things, right? We could do the binomial PDF and find the probability that a household has no cars, the probability that has 1 car, plus the probability that has 2 cars, plus the probability has 3 cars. Because remember, strictly less than means we don't include the 4. So we can go ahead and do a binomial PDF for each of these and then add them up. But don't work harder, work smarter. So if you read a little bit below, we're going to see a nice little feature in our calculator once again for binomial probabilities for x less than or equal to. Now it's not exactly ours because ours is less than, but we know all the tricks that we did in our inequality worksheet, so we're going to go ahead and rewrite it so we can use this function in our calculator, which is similar but not the same, and we call it a binomial CDF, in which you still need to know NPX, but it's just CDF. And what this means is binomial cumulative distribution function, meaning I'm adding a whole bunch. It's cumulative. So let's figure this out. If here is a number line. Here's 0 through 20, right? The trials. Here's 4. And if I want less than 4, here's 1, 2, 3. I want 0 through 3. So the probability that x is less than 4 is the same as the probability of x less than or equal to 3. Because again, we're a discrete, remember? It's counting numbers. So we go to the next lowest integer that'll be equal to, right? Because we would have included it anyways if we were adding them all separately. Well, let's go ahead and use binomial CDF, where the number of trials was 20. Our probability of success is 0.35, and I want my barrier number is 3, because I want it to add every probability 3 or less, right? 3, 2, 1, 0. So let's go to our calculator and go again to second vars and go down all the way till you see binomial CDF. It's right below the PDF. And again, C stands for cumulative. So again, I would do 20.35. And now this x value will be that barrier where it says include the 3 and every integer less than, every whole number less than, right? 3, 2, 1, 0. And hit enter. And we get a probability of 0.0444. Or 4.44%. So the trick is always to play with the inequalities, and I emphasized this in class last time where we're going to have to use inequalities to use our calculator. Now you could do binomial PDF for each one of these, right? And add them all up, you'll get the same thing. Or you could use the formula for each one. But I think that's just too much work. It's working harder, not smarter. And you're just kind of taking more time when you have access to the calculator that's a really it's high functioning calculators, right? So let's try to play with the inequalities a little bit in the next example. It says that using the same example, what is the probability that at least four have three or more cars? So now we're talking about at least four. So again, we had 20 trials. The probability of success was 0.35. And in this case, we still have our little x. We're still observing little x to be 4. But now our big X, meaning our event of success, wants to be at least 4, meaning at least 4. So less than or equal to. Oh, no. At least 4, greater than or equal to. And so if you need to see the number line, we can do the number line. Here's 0, then 20, here's 10, and here's 4. So at least 4 would mean that it includes 4 and everything more. So this way, I could say, okay, the probability of the event of households having 3 or more cars is at least 4. Would be equal to the probability of 4 plus the probability of 5 plus dot 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 plus the probability all the way out to 20. Can you imagine doing all those binomes PDFs or the binom or the actual formula? No way. Let's play with inequalities. The probability that x is greater than or equal to 4 is the same thing as, well, how about this whole probability of 100% minus this little shaded area to the left of 4? So remember, the entire probability is 100%, or in other words, the number 1. But couldn't I just find the probability that's this shaded area, 3210, that all of this, and subtract it from 1? And that would give me the leftover, all the things in pink. So let's do that. This is the same thing as saying 1 minus the probability of x less than 4. In other words, 1 minus the probability of x less than or equal to 3. Well, I have this probability. I found it was 0.4444 in the previous part. And that was well, we could just do it. 1 minus 0.0444. And we get 0.9556.